Welcome to this evening's edition of Shield Instructional Videos. This is the second video on rotational motion, or this is the video about torque. So, the objectives of this video. First, we want to identify, explain, and look at what torque is. Our second objective is that we want to be able to calculate torque for various situations. And our third objective is that we want to be able to apply the concept of torque to situations of static equilibrium and use torque in order to calculate some fun things and be able to balance stuff. So what is torque? Torque. Torque comes from a Latin word meaning to twist, and so it has to do with rotational motion. And basically the torque you can kind of think of as the rotational analog of force. And so just because force causes an acceleration when we're looking at things like cars, a torque is going to be what causes an angular acceleration when we're looking at spinning objects. And so it's going to be really important for this unit because everything that we are looking at that's spinning at one point was caused by a torque. And if you want it to stop spinning, you have to apply a negative torque in order to get it to stop spinning, or at least an opposite torque. So to start off looking at torque, okay, here we have three doors, and you're looking at this door like from above as if you were a bird perched on top of a roof and looking down. So that little yellow thing is the doorknob, and obviously, you know, this is the hinge over here right there. That would be the hinge. Okay, so each of these doors are being opened. Okay, let's say on the first door I'm pulling on the door like by the hinge. Okay, the second door I'm pulling kind of in the middle, and then the third door I'm pulling out on the outer edge on the doorknob. Okay, so the question is, which of these doors is going to open up the fastest? So hopefully you are sitting there thinking about it and not just trudging on through the video. But this door obviously is going to open faster. In fact, this door isn't even going to open at all. I mean, I guess you could try, but it would be really, really difficult to open a door by the hinge. That's why we put the doorknob on the other side. I know, you learned so much in this class. Okay, so now let's ask or look at it a little bit different. So we have the same three doors again. Okay, and so I learned from my first experiment, pull on the doorknob. Okay, on this doorknob, I decide to pull in this direction. On this doorknob, I decide to pull straight forward, and on this doorknob, I decide to pull out that way. And the question, same question again, which door is going to open up faster? And so again, when I put it this way, you know, it's fairly obvious that this is the door that's going to open up faster. You get the most bang for your buck as far as how far you're pulling, because these other two, because of the angles at which you're pulling them, you are either pulling towards the door or away from the door, which isn't actually going to be opening it. Like you can push on the door, you know, you could push on the door from this angle, like onto the edge of the door, and it wouldn't do anything. So because you're pushing like onto the edge of the door, and that's not going to do anything, what we get is that if we want to get the maximum torque or rotational movement from a force, we need to make sure that the force is 90 degrees, okay, to whatever we're trying to turn. So that 90-degree angle is going to be really important later. So tuck that in the back of your mind, okay? Let's move on. So, so if I have a door, okay, and I'm pulling on the knob with the force F, okay, because it depends on how far along the door I was actually pulling, like, you know, am I pulling over here by the hinge or am I pulling over here by the knob? Because that's important, that means that how far we're pulling is going to affect our torque. So if we have a certain distance from what we call the axis of rotation, and that's just wherever I'm pivoting, okay? It's also called, sometimes people call it a pivot point. Okay, it's wherever my rotation is starting from, or like it's like connected to this pivot point. Okay, the distance between that and the force we call r for the radius, and the force, you know, we still use the capital F, and it creates what we call a torque. And so this green arrow kind of represents that the door wants to twist open because of that force. And we use the Greek letter tau, T-A-U, which is that little squiggly T, to represent torque. Okay? And torque is just simply the product of the radius and the force. So it's R times F. So however far I am away from the pivot point times the force that I'm pulling it. Okay, and that's, you can see tau a little bit clearer. It kind of looks like a pie, you know, like this would be like a pie. But somebody kicked its leg out from under it. Sorry, pie. So this represents torque, and the units are Newton meters because you're multiplying newtons and meters. They get married, they hyphenate their last name to Newton meters. Okay, R is the radius in meters, and F would be the force in newtons. Okay, so now that's pretty simple, and there's just one little more kind of chunk that we need to add on to there. Okay, and that's that if I'm pulling at an awkward angle on this door, like I was earlier, and I can measure that angle right there that I'm, you know, pulling off. I'm like pulling off at this like awkward angle. What we did in class at one of your stations was review trig, and this is why I had you review trig, because if you remember way back when we talked about vectors, that force F is made of these dashed vectors. Kind of think of these two little mini vectors or components add together to create the big force. Okay, if we call one of those A and B, okay, that means only A is actually creating torque, meaning that only the force pulling perpendicular is actually doing anything. You know, B is just pushing against the door, which isn't actually going to spin it. You know, you try just like pulling on a doorknob in the direction of B, and you're not going to successfully open a door ever. Okay, because A is the opposite side of our triangle, if you move the angle, that means that we need to have a sine theta term in there if we are given an A or force at a different angle. So then our real torque equation becomes that torque equals RF sine theta. But there is a caveat on that angle, and that's that the only time, well, the only angle that you're allowed to use is the angle between R and F. So if they give you a different angle, you have to use your geometry, you know, either like, you know, parallel axis theorem where you have the two lines and this is equal to that. You got to use your geometry skills to find the angle between F and R. For example, if they gave you this pink angle up here, okay, that pink angle would not be the correct force, or not be the correct angle, because that's not the angle between F and R. Okay, that's the angle. Let me see if it'll go backwards. There you go. That's the angle between F and A, which is not anywhere close to what you actually want to do. So that's not the angle we want to do. We want this angle, the theta, that's between the F arrow and the R arrow. Okay, that's the angle that we want. Okay, so fair enough. So let's look at this in action. Okay, let's say I have a bolt. If you've ever tried to screw in a screw or a bolt with your hands, you realize that it's actually pretty difficult to get it really tight. So torque actually enables us to put more rotational force and power on that nut. So that's why we use wrenches and screwdrivers, because it increases our mechanical advantage. So instead of just trying to tighten this bolt with my hand, you know, I get a wrench. Okay? And that wrench is going to give me more torque than my finger would, because I'm increasing the radius of how far away I am from that bolt. And so that's going to give me a bigger torque. So let's say I'm pulling with, like, you know, I'm prying this off, and I'm pulling with a force of 20 newtons, and the length of the wrench from the bolt to where my hand is, to where I'm pulling, is 10 centimeters. Okay, and the angle between those two vectors is 70 degrees. Okay, first of all, I need to convert that to 0.1 meters because it's in centimeters. Okay, and then I want to find the torque. So I'm going to use RF times sine of theta. So that means torque is just 0.1 times 20 times the sine of 70. I kind of set it all up, so it was really nice. Okay, because we like to do easy problems before we really get messy. Okay, and I get 1.88 Newton meters as my units. Again, because I'm multiplying Newton and meters, I just do that against my computer. You get Newton meters. So the next question, what if they ask you about direction? Okay, well, so if you think I'm like grabbing this wrench and I'm pulling it, I'm creating a torque in the clockwise direction, which we use as CW. And that's probably Clay White knocking on the door for class. Too bad. Okay, so if I have a box here and I'm pushing, so this is a couple of examples is where torque comes into play. So let's say that I have a box here and I'm pushing on this box. Okay, the radius, you know, when you push on a box, sometimes they like tilt on that far corner and they will kind of topple over. So if that's the case, then that means you're creating a torque. And the radius would be from that pivot point to the force. So in this case, it would be the diagonal of that box. And you'd be creating a torque, you know, in that direction. Okay. Another example where torque is used is the little mobile that sometimes people hang over their cribs, you know, for a little baby, and it makes them preoccupied, they don't cry, and you win as a parent. So if you have a mobile, okay, both parts of the mobile are pulling down with the force of gravity. So you have these two forces, and from the pivot point, which would be wherever that string is attached, you have these two radiuses. So that means each of these sides is creating a torque. Okay, and so the whole point of a mobile is that those two torques need to be balanced and equal if you don't want it just to collapse on your child. Another example of torque would be in the area of gears and sprockets. So let's say this is the back, you know, this is the gear on your bike, and there's your chain. Okay. Your chain, when you press down on your pedal, is going to pull with a force, okay, on your gear, and your gear obviously has a radius, and so then it's going to create a torque, and you get to bike to school or whatever. So these are just some examples of where we see torque, especially in physics problems. Okay, so the last thing that we want to talk about in this video is about equilibrium. And so there are two conditions for something to be in equilibrium or in an equilibrium state. And the first is that all the forces have to equal to zero, or that there's no net force. This was like way back in September when we talked about balanced forces and like I'm not accelerating at all, or I'm just sitting here, I'm moving constantly. That was the first condition for equilibrium. But now that we've talked about torque, there's a second condition, and that's also that I cannot have any net torque. Because I might be sitting here with no net force, but if somebody is putting a torque on me, then I'm still not at equilibrium. I could be spinning instead of, you know, being at equilibrium. Okay, so this is really apparent if I, like, you know, took a meter stick and I balanced it on my finger. Okay, if I'm balancing a meter stick on my finger, okay, the forces are equal. The normal force provided by my finger is equal to the gravity force pulling down with the meter stick's weight. So excuse me. So that first condition is met by no net force. Okay, but there's also two kind of balancing torques, and so these two torques also have to be equal. Otherwise, we're not going to be equilibrium, and the thing is going to spin off my finger. For example, I could put a heavy weight over here, and the force would still be balanced, but the torque would not, and so the ruler would fall off my finger. Okay, so we're going to look at this a lot in one of your stations on Wednesday and Thursday, is, you know, balancing and equilibrium, and your lab on Friday is going to be about this too. Okay, so let's look at one last example. Okay, let's say I'm at a playground and there's a seesaw, and I get on the seesaw. I'm like a small kid. I only weigh 30 kilograms, okay? And let's say I'm 1.5 meters away from the pivot point. The pivot point in this case is the center of the seesaw where it rocks. That would be the pivot point. So I'm sitting there, and then, you know, Alberto, who weighs 80 kilograms, is kind of scary, comes up and he wants to get on the seesaw, okay? So the question is, where does he need to sit so he doesn't just completely send me flying off the seesaw. Because if he sits on the other side, right, we are not going to balance, and I'm just going to fly up, get stuck, and then never be able to get back down. So I want to know, where does he need to sit over here on the seesaw in order to balance out, and so I have a perfect balanced seesaw, okay? So the trick is that when I'm sitting on the seesaw, I've already caused a torque. And that's why I'm like sitting over here on the ground, because I've already moved the seesaw down. Now when Alberto gets on, then he's going to want to move it the other way. And so we have to balance these two torques on the side. So if we want them to be balanced, that means I need torque 1 to equal to the second torque. Okay? Well, the nice thing is that when we are balanced, gravity will pull straight down, which means we'll have a 90-degree angle. So that means we don't have to worry about the sign of the angle this time, because the sine of 90 is just 1. So that means I have RF1 equals RF2, because I'm not worrying about the sign anymore. Okay, so my radius is 1.5. My force is my weight, so 30 times 9.8. Okay, and that equals the second radius that we have, okay, times his force, which his force is 80 times 9.8. So when I divide both sides by 80 times 9.8, I get that R2 equals 0.56 meters. So he needs to sit pretty close to the pivot point. Okay, so you can see that there's a balance between his weight and how far he needs to be, away from the pivot point. So because he's bigger, he needs to be closer to the pivot point. And again, you'll see this a lot better in lab than me just talking to you and throwing numbers at you. Okay, so let's recap really quick. Okay, first, rotation is caused by something called torque. Second, torque is the product of how far you are, the distance, and the force that you're applying. Or mathematically, we use T equals, or tau equals RF times the sine of theta. And lastly, what we looked at is that if the torques are balanced, then we have achieved what we call equilibrium. So thanks for watching, and that is the end of your second video.